Raisa, for the introduction, and good afternoon, everyone. So today I want to talk about tension in health and AI. So first, let's start with, what are the promises and hopes and opportunities given the advance of technology in various fronts, actually, that make AI in health possible, right? So on one hand, in the hospital environment and clinical environment, an increasing number of medical devices are now online. So for example, glucose monitoring, a lot of the lab work, electronic health record information about patients are made available, right, for data scientists to look at, as well as wearables. And beyond that, also in the consumer side of things, right, so we have all this wearables that you have access to. Right now, the Fitbit devices can tell you whether or not you have a good quality sleep at night, right, giving you day-by-day report. Right, so these are ubiquitous. And in addition, right, with the advancement of wearables, I have a colleague in my department, Yang Zhong, working on a personalized e-tattoo, right, that is really unobtrusive, and you can do blood pressure monitoring on this wearable e-tattoos and other wearables like that. So it is possible now to collect data in a very not intrusive manner every day, continuously, right? So we have smart sensing and IoTs, which means you can do on and off-site, real-time continuous biometric monitoring. And now with the advancement in AI models that can consume multi-model data, right, and come up with digesting this information and make inference in a practical real time, now we can do autonomous diagnostics as well. Now, moving a step forward, it's also possible to do personalized therapeutics. Right? Imagine, digesting the data in real time and then come up with a decision to control something, right? Actuating. So you can deliver a little bit of shock, right, to the heart area, or stimulation to the brain. So all this is possible, right? So now let's talk a little bit about how to bring these technology innovations to translational research, scale it up to actually make it truly accessible to end users, to the patients. Right? And in working on this, as Raisa mentioned, my background is really computer networks and distributed systems. And since day one when I joined UC Davis in 2002, my whole research is data-driven, except we don't call it big data or AI back then, we just call it internet measurements. Right? So I work with industry to instrument the network in such a way that we can do intelligent measurements of the network in an adaptive model manner using programmable hardware, so that we can do analysis of the data, do diagnostic, and then we can design a better network control or traffic control algorithms. And then with the proliferation of Internet of Things, not surprisingly, my research also kind of branched out into different application domains, including transportation and health. But more importantly, for a personal reason, in 2014, I got very sick, and I spent a lot of time bouncing from one specialty clinic to another, and it made me frustrated that I'm working on advanced computing technologies, and there's a huge gap between that and the health domain, and the healthcare in particular. So that brings me to, the first project I worked on is applying IoTs and Edge AI in the critical care environment. So the first project I worked on was actually in collaboration with Dr. Jason Adams. He's an ICU doctor, and I gave a talk about my anomaly detection work using wireless signal, and he told me, your signal looks just like my mechanical ventilator machine signal. Right? Can you do something to help me? Because he is really interested in doing an early detection of what he called ARDS, acute respiratory distress syndrome, which is really wet lungs syndrome. And typically, among the patients that are in the ICU that are put under mechanical ventilator, about a quarter of them eventually kind of develop this ARDS, and it's life-threatening. Even in mild cases, 30% of the patients don't make it. In the serious cases, 50% of them don't make it. And he wanted to be able to detect it early. Now, the current way of doing things is you have to wait until the physician, right, in his case, when you do the ICU rotation, you notice that something is wrong. You will order a chest x-ray, and then you have to wait for the chest x-ray to come back, and radiologists look at it and say, oh, it meets the Berlin criteria. This patient is the ARDS condition, and you need to do But by then it might be too late. So his idea was mechanical ventilator. Once you put the patient under, you have a continuous signal, right? And there's an objective signal that you can already collect and train on. So this is the first project that I worked on. And we have really good results, and it turns out that it was timely. We did this work in 2016 and 17, and then COVID hit. And properly kind of detect and realize which patient has the danger of developing ARDS is very important for triaging and for hospital management as well. And then moving from there, we're also looking at the NICU environment. This is a newborn. The doctor that I work with had this because he's interested in looking at critical congenital heart disease detection for the newborn before they are discharged to go home. Because again, if you miss the detection, by the time you come back, it's often too late. And so we look at the dual lead measurements, and these are just pulse oximeter. We try to look at the continuous waveform to detect the condition. And then for the back end, I have a collaborative project with the Alzheimer's Disease Center, trying to look at applying computer vision algorithms as well as deep learning algorithms to the whole slide image of brain tissues to do a deeper phenotyping of neurodegenerative disease like Alzheimer's disease and dementia. And then lastly, I also have a collaborative project with the Mike Institute looking at the videos of the children interacting with the providers in their clinical settings in order to detect complex behavior that are associated with autism. Right? So whether or not the child is looking at an object, whether or not they're looking at the provider, whether or not there is a social smile given. So the reason I point out these various kind of projects at a high level is because I just wanted to use this as case study for the rest of my talk to talk about a few tensions, right, that are observed. So the other, really the research that I've been working on in the past few years are really experimental research in terms of how do we solve scalability problem, right? When we apply IoTs and edge AI to critical care or hospital environment, there are security, privacy, and robustness issues that we have to look at. As you can see, the video data is very sensitive, right? So we need to look at privacy-preserving queries of this information as well as synthetic data generation potentially in order to share our research results and tools with other researchers. And then more importantly, a lot of the medical data that we work with, right? The data set is pretty small. The label data set is pretty small because it's so expensive in terms of the annotation cost is quite intensive, right? Expensive because it involves a lot of human domain experts in order to help us annotate the data set. All right, so Raisa told me, to talk a little bit about attention. So over the past few years, right, a lot of these projects are grassroots. 2 years ago, when we have the college has this new research, next level research vision, I actually led a team of colleagues from College of Engineering in partnership with UCD Health, School of Medicine, and School of Nursing researchers. We're trying to basically come together, right, to see if we can build better synergy so that we can scale up the effort and to make these smart health solutions truly accessible to all. And so for the rest of my talk, I just want to kind of share with you some of the tensions and challenges that we have encountered, and I hope I'll be able to get some advice from you as well. So the first concern I have is a widening digital divide, right? So being a technologist, I'm observing this, right? So AI has two wings. On one side is data, the other side is compute. There is actually a running joke. If you can double the amount of data, double the amount of the number of parameters in a model, you have a state-of-the-art model, right? You can publish in NERIPS, in CDPR, right? Now, so this is the dimension we are looking at. So 12 years ago for LXNet, right, that is kind of a cornerstone, one of the cornerstone, because back then, it had become practical to run real-time image classification using deep learning model by LXNet. It's 60 million parameter, and it's trained on 1.2 million images, right, with the notation. Now, fast forward, Llama came out last year, the first Llama, this is Llama 3 this year for Meta, right? This is general purpose foundation models who can do vision language queries is 70 billion parameters, and it was trained on 15 trillion token, right? Now, this is a chart that I borrowed from IEEE Spectrum article about the 15 charts that explain the state of AI in 2024. Back in 2017, when Transformer came out, it cost $900, right, to train it. Now it costs millions of dollars, right? Now, besides the cost, the computing cost, this also costs us in terms of carbon footprint. And sometimes I do feel guilty because I work on AI in the AI field. And for a lot of this to happen, right, I wish there is a solution where we can sustain this advancement in AI without burning out the planet. Now, what does that mean though? I mean, the digital divide comes in many forms. One is even as an AI ML model developers, training this kind of foundation model, 7 billion. In fact, actually there is a 400 billion parameter model that is still training. Remember, it still hasn't released it yet. It requires vast resources. Now, industry is now leading and dominating the scene. Right? Google is number one in terms of outputting foundation model. Can academic labs reproduce, not forget about training, even that. We already know we lose the bullet train, but can we even reproduce and adapt these models, right, for various societal skill problems that we want to look at? Second, for AI in health research, right, to really scale and to be meaningful, we need interpretable models, which means we need a lot of different kind of support for true team science, right? So when I say true team science, it means embed PhD and master students in the college, from the College of Engineering in the health side. Like for example, when I work with Dr. Jason Adams or Brittany Dagger, I have students who spend time taking this training on the health side, go with the ICU doctor to do the ICU round. They see for the first hand what the doctor has to deal with, and they have to work closely with the doctors in order to understand the signals. How do we scale up this type of fully immersed training? I mean, that is a question I have. Now, second, I mean, in terms of the health provider and practitioners side, I mean, I have received a lot of inquiries these days about consultation about how to use AI for their specific health problem. Now, and I observed some of these, right? Some are concerned about job security being replaced by AI. Some are skeptical, they don't want to touch AI. And then there is also a camp of overzealous practitioners about AI. The first thing they ask is, oh, can I just use AI on my model? And my first question to them is, why do you think you need AI? I mean, there are some problems that are simple problems, small data set. AI is not a suitable solution for you, right? A logistic regression model works equally well, and it does not chew up a lot of resources. And so what we are missing really is a research concierge services, right? That API between technology and health for us to find the right solution. And then patients also, I mean, there is kind of a digital divide there as well. A lot of our patients are from the underserved community, right, in a wider Sacramento region. They don't even come to the hospital. So a lot of these advancements that I was talking about in the previous slide, if they are not even at the hospital, they are not going to benefit from it. So what can we do to help them? Now, of course, there are other problems as well, and I'm not an expert. There are liability issues, accountability issues, bias, fairness, adequacy issues. So what do we do in this space, right? So back in that simple example, right? We want to look at the mechanical ventilator waveform, and then we want to look at, how do we translate that into a solution. We make great progress in the hospital environment, but our next step is, can we actually package it up in handheld solution, which is possible, right? So with the Nano Jetson Nano that came out from NVIDIA, we can actually run a lot of the AI inference model on a credit card size device. And this can be packed up in portable platforms and be used in mobile clinic and be used in the community clinic. Now, that's the good news. Now, what's my concern? Well, you have sensitive medical data, your sensitive inference result, whether or not you have the diagnosis, positive or negative diagnosis is sensitive. You have AI ML model that are proprietary. And now you're running on small devices, edge devices, they are power, compute, and memory constrained. This is a security and privacy nightmare. In fact, my group has identified some vulnerability, right? Even with a small device, with side channel attack, you can infer the result. Or you can actually fingerprint the type of AI ML model that is running on this model and then launch downstream attacks. And this is not just kind of a problem on the edge. If you look at the entire ecosystem, right, you are gathering data at various points in the hospital network, and as well as gateway, and then you go send it to the cloud for training, and then you send it to the scaled down AI reference model on the edge device like a smartphone. Every point along this, right, is a potential attack surface. Right? And attacks on IoT networks is not new. I mean, this news came up many years ago already, that this is a thermometer, right, for a fish tank, but it became, once it's compromised, the attackers now have access to the casino's database. Now, another news that came out about ransomware, right, medical devices, ransom, is not new. I mean, these problems are there. Now, why is it so hard? What makes hospital network vulnerable to IoT attacks? Well, I'm a networking person, right, so I'm kind of intrigued by this problem. Well, first question is poor device visibility. There are so many types of IoTs and wearables and medical devices that could potentially be online. And the quantities is a lot, right? And you don't even know what is in your network and what it functions. Now, second is bad IoT network segmentation hygiene. This is a typical realistic hospital network on a VLAN. You usually partition the network by VLAN, right? But they either partition it by default based on the device manufacturer or by floor. So this is one example where the network is partitioned by floor. So look at what is there. You have camera, you have glucose monitor, so you have medical data in there, patient data. Some are sensitive, some are not. And then you have printer, you have computer. If your printer get compromised, you have access to the surveillance camera. Right? That's sensitive use of data. All right, so back to the question about tension, why I say true team science is needed. This is a typical pipeline, right, for AI ML model development. You get the data, you need to understand what the data represent. You need to work with the health professionals, right, the domain expertise in order to understand what features should I extract from the signal, and then train the model, and then you probably validate the model. Now, it turns out that in AI in health project, a lot of the time, the most time consuming is actually that front part, right? Getting the data out and then truly understand what features should I extract from the data and use those features to train the model. Now, why do we spend so much time on that? Well, this is just a simple example, right? Blood pressure waveform, and then you want to detect the dichrotic notch. Well, true data is very, very messy, right? And these are all of the other examples of how do you figure out which one is a true dichrotic notch. You can't just give the data to the student, they go off, produce a result, and then you assume that worked, right? You have to have constant conversation with the doctor. Second is we have limited annotated data set. So I will jump ahead to kind of look at, talk about that in a second. Now lastly, we really need to validate and test our models for generalizability, producibility, fairness, and robustness against adversarial attack as well. But it's hard to do because right now there is no standardization and open research forum for this. One of the challenges that we have is a lot of the sensors and medical devices run a proprietary protocol. There is no common API for us to get the data out. So even when, we're back to the problem of getting the data out of pulse oximeter devices, whenever we get a new set of device, we start to worry. I mean, are they going to have the same protocol? Are we going to have to rewrite the API to get the data out? And the timestamp as well. And then secondly, we need community building in order to, because a lot of the data sets and tools are developed in individual labs. So we need a way to actually share these tools and validate them. And so just to fast forward to that point, now why do we need that? Sometimes you might think that our end-to-end pipeline work very well. You can do, the image participation, segmentation and plate detection pretty well. But then when we get different sets of data from different labs, because it's different scanner, different compression ratio, different format, now the performance get a hit, right? So we need to properly validate that. Second, when we are dealing with small data set, again, because data set is so hard to come by, we actually have to look at ways to do data and label efficient deep learning so that we can have pretty good results with small data set. And then lastly, these are just the examples of how Llama still cannot solve this problem. This is a patch showing pathology. We asked Llama the simple questions of, does it have, do you know if it's gray matter or white matter? The right-hand side is the Llama answers. Unfortunately, all this is incorrect. Okay. So there is still a ways to go. And this is basically, I'll end with this. This is our dream. We're trying to build a brain bank, collaborating with multiple institutions to collect data sets, and then we are going to do cross-site validation of our tools and our data. And then lastly, I just want to have a shout out to all my partners in crime. And I learned a lot from my collaborators in School of Medicine. And there are too many names to be fit here. So. Thank you.